So welcome everyone to the Learnathon22 computer vision workshop. So my name is Edward. I'm a second year software engineering student at McGill University in Montreal. I'm really affiliated with Curious, so you might have seen me on the Discord server if you're active. And I also do a few activities, other activities during Learnathon. In fact, we have one tomorrow where we'll do a live devlog. So feel free to come if you're available. It's at the same time, 7:30 EST. So I'm welcoming you already. You have here my LinkedIn. If you want to add me, that's okay. I'll accept it. And yeah, so we'll be talking about computer vision. So computer vision, just to let you know, is a very large topic. So to start, we're not going to cover every single aspect of it. It would take more than an hour and a half to do so. So we're just going to really walk through the basic introduction, and we're actually going to do some ML project at the end, which I think will be really interesting for you guys. You don't need any specific knowledge. I would expect you though to know a little bit of Python. It's really the minimum I require you to know. Otherwise, you should be fine for the rest of the workshop. Also, if there's any question, feel free to ask me, because like I said, I'm not going to cover every single topic. I'm going to go in some aspects, I'm going to go very broad. So just ask me a question if something is not clear. So to begin with, what is computer vision? I think it's important to understand what we're working with. So computer vision is really anything that has to do with processing or analyzing video or images. So really, there's a lot of, especially in ML, it's a very large topic. There's a lot of subjects that use computer vision. You may not even realize that it uses computer vision, but as long as there's some kind of processing or analysis of images or video, that counts as computer vision. Computer vision itself can also be, I've been talking about analysis of images. So that can be classified in three different ways. So we have classification, which is just about recognizing objects in the image or video. So as we can see here on the left, we have a dog. It recognizes that it's a dog, but it doesn't give us more information about it, just what type of actor is or object is in the image. But we also have a more detailed one, that is detection. So this is a little more advanced. It tells us it's classification, but it also gives us another a piece of information, which is the location of the actor or object inside the image. So here specifically, we're able to crop the image and determine that this part of the image contains a dog. And finally, we also have segmentation, which is another very important part of computer vision. This is really about cutting off entirely the subject. So if you think of it like if we were to make the background transparent, you would only have the object or the actor itself that we're interested in and nothing else. No other pixel in the image should be in that segmentation. So like I said, yeah, and AI it's really, computer vision is strongly related to AI. It's actually one of the first one of the first AI projects that was ever created that we'll actually talk right now about. So computer vision is really, really old. You were probably not born at that time. You're actually maybe even not even your parents might not have been born at that time. Your grandparents maybe. So one of the first computer vision projects was the Mark I Perceptron by Frank Rosenblatt in 1958 at the Cornell Aeronautical Laboratory. So a perceptron, just to let you know, is a very simple machine that is capable, or software that is capable of classifying what object it's seeing. So it's really about perception. That's where the name comes from, perceptron. And actually, you can see the machine here. This was actual hardware, so it was not done software. It was entirely done hardware via electronic circuits, analog circuits mostly. There was very few digital at that time. It was still brand new and not yet a convention. And yes, this machine was capable, contained 400 photocells, so it could analyze images of 400 pixels and determine what type of object was present or it was looking at. And it used neural networks, so it was really some deep learning that was done here, but because it was not done software, all the tangled wires that you see here in the image is really just a neuron connected to another, and you have this whole bunch of mess that made it so that the neural network could actually function. So it was entirely hardware, and these switches on the right were potentiometers that you could use to adjust the weights of the different nodes and the different neurons in the neural network. So yeah, it was a lot of manual labor, and it was not super powerful. You know, there's only a few details you can get from a 400 pixel image, but it was again one of the first attempts at building a computer vision project that was actually useful. So other application in computer vision, of course, we have navigation. That's probably maybe the most common one, or the most obvious one, I would say. One of them is self-driving vehicles. So if you probably heard of Tesla, how it has inbuilt support for driving self-driving. It's not fully autonomous yet, but they're coming close to it, and it's actually very powerful. It can really do incredible stuff, and it has a really fast reaction time. So we might be able to see more of those in the future. We also have unmanned vehicles. Here I have an example of the Mars rover Perseverance that landed about almost 2 years ago. So because having aircrafts or vehicles on other extraplanetary locations, it's really hard to control it live. So you cannot have just a pilot that pilots the landing vehicle for the rover. That's impossible because there's a 15-minute delay between Earth and Mars communication. So you really have to have a really reliable system on board that uses cameras to properly land the vehicle at the right spot that it was programmed for. So yeah, if you're really interested, there's a bunch of videos. Actually, this rover specifically had onboard cameras, so you can actually see what it saw live, which I really encourage you to look for. It's actually very, very interesting. Another very popular application that's getting more and more reliable, more and more important for our future, especially in healthcare, is how computer vision is capable of analyzing, for example, CT scans. So like we talked, like we talked previously, so it does some image segmentation. That means it really isolates parts of the image, pixel by pixel, and it's capable of detecting things such as diseases or specific signs that would indicate a certain effect on the health. So here specifically, it's from a research paper that was analyzing COVID in the lungs. So really they segmented a patient's lung to detect the presence of COVID. So again, this is getting really popular. It's done also with the brain for tumors. So it's something really at the edge of our technology. Of course, there's also medical training. So humans have forever, if you're studying in healthcare, if you're studying medical, you probably have to dissect at some point. Well, imagine instead of dissecting a live body, which sometimes can be a little bit hard to provide, or there's less error, there's less place for handling errors. What if instead you could have a hologram, or you could work with virtual reality or augmented reality to basically dissect virtually and learn virtually how to do medical procedures. So this is another thing that's been very popular, and that will probably become a standard in a few years. Another, and the last, I think, application, there's a lot more of applications, of course, but I think this is another very important one. We have agriculture. And everything that's related with territories. So you probably heard of drones that are used in agriculture just to because fields are huge. They're huge. They're very long. They have a lot of kilometers to work with. So sometimes if you want to keep a check on your plants and keep a check of your whole fields, you would need to have a drone that would basically analyze the health of your plants. So this is something that has become really popular. So if you're a drone pilot, this is probably the way to boost your career, if that's interesting for you. There's also satellite imagery, again, that can be used for agriculture, can be used just to detect all kinds of stuff. Think of Google Earth. So it's a very powerful tool to analyze quickly what's happening on an image. So to begin with, for this workshop, you'll need 3 tools. So like I said in the very beginning, we'll be using Python as our main language, and we'll be using 2 additional libraries mainly. We'll have Opencv and TensorFlow. Opencv is the Open Computer Vision library. So it's an open source library that has a bunch of tools very useful for image analysis. And we also have TensorFlow, which is another very powerful tool used for neural networks and machine learning in general. So I'll be using Windows mainly. Everything should also be working on Mac OS and Linux with a few variations. Just let me know if you have any issues and we'll try to fix it. So to start, you need to install, we're just going to call python-m pipe. On some computers though, on Linux, for example, you might not need to do the python-m. You just start with pipe. And then we specify install to install the libraries that we want. So we want to install a few of them. So we're going to install NumPy, which if you've done the previous Python workshops at the beginning of Learnathon, you should have it already installed. If not, you'll do it right now. You have Opencv. So Opencv is opencv-contrib-python. Make sure it's not just Opencv, that will not work properly. And we'll also need TensorFlow. So TensorFlow is a bigger library. It's about almost half a gigabyte. So that's why I would recommend you to already start downloading it right now, especially if you don't have a very fast internet. And we're not going to use it right now. We're going to go a little bit of more theory just to understand what we'll be working with. But at some point, we'll have to use TensorFlow at the very end when we'll build our deep learning model. So just press enter. It's going to install everything. I already have the packages installed, so it will just say that the requirements were already satisfied, but just make sure that you have it. So we're talking about images and videos, but what is really an image and a video? How is that? How does a computer recognize one and how does it handle it? So to begin with, let's assume that we have this grid 6 by 6 pixels. So we have 36 pixels in total. And let's assume that for each grid, for each cell in that grid, we'll assign it a value of 1 or 0. So here we have a small smiley face, and we want to basically keep it stored somehow on the computer. So what we're going to do is that we're going to basically give an index to each basically pixel in the image. So the top leftmost pixel will be 0, and the bottom right will be the last pixel, the 36 pixel. But because we're starting with an index of 0, the last one will be 35. And each pixel will either have a value of 0 or 1. So it's a binary. We have a binary system here where there's no in between. There's no 0.5 or 0.6. It's just 0 or 1. So if you want to represent how a computer would represent this is through an array. So in Python, this is what it would look like. So we have a 2-dimensional array with each row being a set of numbers, either 0 or 1, depending on the pixel value. So as you can see here, we have zeros for black and 1 for white. So this is how we're gonna basically assume that for now that the computer stores a basic image of 1s and 0s. But of course, this is not always the case. We already know that there's more than just black and white, and there's more than just pure black and pure white. So how would we vary the shade of this color to have something like gray? So here we have very similar situation, but instead of having either a binary value of 0 or 1, we're going to instead assume that it's an integer value. It's an 8-bit integer. So that means that it can be a value between 0 to 255, as you probably know how 8 bits how bits work. So that's how we're going to store the image. So again, same thing. We're going to segment the image. Each pixel is going to have a different index. And we're going to assume that this is how you're going to build it in Python. So it's very similar to your previous to a previous representation of an image, but instead of using 0 or 1, we can use any integer between 0 to 255. So 255 being the brightest pixel, being a 1, and 0 being equivalent to black. So we have here a smiley, but we also have gray, which is represented by 250. It's a number in between 255 and 0. So it's just gonna be some shade of gray. Okay, great. We can now kind of work with luminosity, but how can we add color? That's what's interesting, right? So let's assume that instead our smiley face is yellow. So how are we gonna handle this if we don't have any gray or black pixels? So what we're gonna do is that instead of assigning one single value for each pixel, we're in fact gonna assign a few of them. So our image that was previously handled as a 2x2 array will now be worked with as a 3x3 array. So each pixel, like I said, is gonna have a vector that's gonna have 3 values in it, both a red, a blue, and a green value. This value will be stored as a 8-bit integer. So again, we can vary each color's intensity from 0 to 55, but we have to keep 3 separate values for each pixel at all times. So we're going to call one of those values, either blue, green, and red, we're going to call these channels. So each pixel has 3 channels. So again, this is how it would look in Python. So it's getting already bigger. Now, instead of having just a 255, 0, or a number in between for each pixel, we have another array that has 3 values in it, a vector representing each color channel. So this is basically how we're going to handle, this is basically how images are going to be handled in our in Opencv and later in all our projects. And just a reminder, notice that this is, even though we might conceive images as being 2D, this is for a computer, that's not the case. It's actually 3D because of the additional color channels dimension. So to begin with, we're just gonna load an image. So we're gonna see how Opencv is capable of loading an image. So first of all, we're gonna have to import a package. So we're gonna say, first of all, let me know if you can actually see my screen, because I know sometimes it can be a little bit more pixelated. So just let me know if you can read the text. Okay. Okay, thank you, Alex. So I'm just gonna import Opencv2 after it's installed. So this will allow me to access the library. I'm actually also gonna import for later on NumPy. So import NumPy as NP. And that should be all about it for now. We're gonna need TensorFlow, but this will do it in another different notebook, which will cause less mess. So we're just gonna execute this. So we imported both libraries. We're also now gonna read the image. So to read an image with Opencv, it's actually very simple. So I already have preloaded here a few images. I have both a dog, a house, and I also have a video, which we'll use later on. But feel free to use any image. I recommend you using a JPEG. It's a lot easier to work with. And also because we're not touch transparency, only use 3 color channels, red, green, and blue. We don't want like a 4th channel for transparency. It's a lot more complicated. So just make sure that they're JPEG, and that should do the trick. Any image would work, by the way. These are just examples. So to load an image, we'll just create a new variable here, and we'll call Opencv2 image without the G, and image read. And we're going to specify the path of the image. So in this case, as we can see here, I have, for example, the dog. So I'm just going to bring in the dog.jpg. And basically, this will load into memory the dog file, the dog image. If you want to display the image, it's very easy as well. We just call cv2.image im show. And then you have to pass 2 variables. Because this is going to bring a new window, you're going to need to specify the name of the window, which is basically the equivalent of the ID of the window. So I'm just going to say dog. And the second variable that I'm going to pass is the image that we just loaded into memory. So if I were to actually start this, it's going to probably crash. Yeah, that's normal, because what's trying to, or if you're not using Jupyter Notebook, it's probably just gonna end the program immediately. So you don't want to do that. It's not gonna be useful. I'm just gonna close here. It's gonna crash. This is fine. So I'm just gonna reload these two libraries, and I'm gonna load again the image. And after I show the image, I have to keep the window open. So that was the issue why it crashed, because it didn't keep the window open. It just quickly closed the window, which caused an error, and it didn't exit the program properly. So what we're gonna do is that we're gonna do CV2. We're gonna put wait key, and we're gonna specify the delay of the of how long you wait after you launch it. So that would be 0. We want it to not wait, just close the program immediately. So we're gonna call this, and we're actually gonna be able to see our dog. So that's pretty cool. There's nothing we can do. We can see that the name of the window is dog, but if I try to resize the screen, it's gonna be all gray. Yeah, that's pretty much it. It's not that interesting, but we can now load for the moment images in the in memory. We can also load video, which is also very easy. Video capture, and I'm gonna specify the path of the video. So here we have the path being the name of the file being raw.mp4. So I'm just gonna write raw.mp4. That's good. And then we want to show the video, but showing the video isn't just about image show and it's going to show a window with all the video automatically. You have to do a lot more work. So you can think of the video as being an array of images. So we said before that an image is 3D. It has 3 dimensions. It has both the width, height, and each pixel being having 3 color channels. Well, videos have an additional dimension being the time dimension. So each frame, because you have multiple frames, one after the other, you have that is considered the time dimension. So it's 4 dimension instead. It's kind of confusing having 4 dimension for a 2D video, but this is how computers store that information. So to actually loop for the images, we're going to have to create a while loop, while true. We're going to have a return value. This is just to, we're going to call it, I'm going to write the whole function first. It'll be easier. So we're going to read the frame, and this returns a tuple. So the first value here just tells me whether it was successful in reading the next frame. And the second variable is the actual image frame itself. So then what I'm going to do is I'm going to create a breakpoint to exit this loop in case I want to close it. So I'm just going to write again wait key. Put 1 this time, doesn't really matter, I can put 0. And I'm going to write this weird thing. This is how basically Opencv handles its exit. It's not really important understanding why, because you'll do it once and then you'll never have to touch it again. It's always the same thing. But this just checks whether when you press Q, when you press Q, it will basically exit this loop. So we're just going to call here break to exit the loop. And at the very, very end, we're just going to release, basically stop the video object, the video that was playing, by calling vid.release. So if we actually load this, so CV2 image show, now we'll see it. So we'll call this whatever, let's call this road, and pass in the actual frame. Okay, that was a waste of time. Let me see if it actually, yeah, I think this is dead. Okay, here we go. Let's reload this. Okay, here we go. That was quite a run. So we're basically loading the image, but what we're doing is that this is an error because there's no more frames when the actual video ends. There's no handling of the issue. Like there's no handling of missing frame. That's because frame will turn into none, null, and it will basically try to display an empty frame, which is impossible because yeah, there's no more frames available. So yeah, what it does essentially is it loops through the video, it gets every single frame, and it displays it on the screen here. So close this. Okay, here we go. Okay, we'll restart automatically. So we're just gonna Call this. What I also want to show you guys is that we talked about how the structure, yeah, sorry, I missed. Oh, it's basically a way, this part of the code, essentially what it does is that it checks whether you press Q on your, it's a way to exit the window. So because we're in a while loop, we have to have a method to properly exit from the from the video loading. So what it does is that it detects whether when you click on Q on your keyboard, it will just exit. It will just call break, and it will exit this while loop and release the video. So yeah, it's just a way of exiting the current window that appears. It's nothing more than that. Okay, great. So we're talking about the later before this, we talked about how the where was it here? How an image was structured in the memory. So I'm actually going to show you guys how that's true. So I'm going to call, because the frame itself is stored as an array, actually it's stored as a NumPy array. So if you actually did the workshop at the beginning of the Learnathon, you probably learn about a few ways to use NumPy. So because that's a cool thing with Opencv on Python, is that packages like that are already compatible. They actually use it innately. So we can actually call image.shape, and this will essentially, oops, I have to load the image. Okay, this will actually show us the size of the image. So it gives us both the height, width of the image, and the 3 color channels. So I said that there were 3 color channels to display every single color that we want on the screen, and not just like a black and white color. So this actually shows you how it works. And if I were to actually show you the video, it would be the same thing. You would just have it 4th dimension for every single frame. Okay, now that we've seen a little bit how images work, let's talk more about color. I've been talking about coloring channels, and maybe I mentioned color spaces, but what exactly is that? How does an image use 3 different color channels to represent all the colors that we want to on the screen? So we come back here and just go here to slideshow. So a color space is essentially a set of all possible colors that the computer can display on your screen. So it does that usually by using a 3 color channels, so RGB. That's really the most popular right now, but we have also other methods, other color spaces that do the same thing. For example, HSV or HSL. So those stand for hue, saturation value, and hue, saturation, and luminosity. So these work a little bit different. They have other advantages. I know, for example, HSL are a lot more natural colors, you would say, like how they're ordered, how they're structured together. So that might be a lot more useful if you to use that color space. But just to let you know, guys, today in this workshop, we're not going to use any other color space. We're just going to use RGB. So here on the left also, we have a chromatic diagram. So this is just a diagram that puts every single color on some Cartesian plot. So as you can see here, it's kind of weird. There's this weird shape that appears kind of like a wing or a fin. So here the numbers in blue are essentially the light, essentially every type of, I forgot the word, light, wavelength, sorry, yes, thank you very much. Yeah, every single wavelength that is visible to the human eye. So it doesn't represent every single color possible. It only represents the colors that human can see. So maybe another type of animal would see different colors. This is really specific to us. So that's what what you can see from the blue numbers here. These are nanometers. And we have also above those, we have those triangles. So we have multiple ones. So you probably see Profoto RGB, we have Adobe RGB 1988, and sRGB being a very popular one. So these are different color spaces. So you might see that that different color spaces have different sizes. So every single color that is inside those triangles are essentially colors that you can use that can be displayed using that specific color space. And you can see that different color spaces might have different sizes. Some even go outside of the current of the human visible light, which is useful if, for example, you have a camera that picks up a lot of raw data that you then can compress or reduce to have a more have greater quality to your image or greater colors. So different color spaces give different tones to the to your images sometimes, and we can also convert different color spaces and so that's why we're going to actually see in OpenCVs that we can actually convert different color spaces, which can be very useful in certain places or in certain applications. But to be honest, the most popular one is probably RGB, and that's what we're going to work with. We're also going to work with monochromatic images, so black and white. So instead of having 3 channels, it's just going to have 1 channel, just like we talked at the very beginning here. So this is the other type of image with which we're going to work with. Why? Because they're simple to work with. They only have 1 value per pixel. And sometimes, you don't need colors to necessarily process the image. Sometimes just the actual shape or shadows of what's happening is what is required. So I will show you how to actually convert from different color spaces. It's very simple in OpenCV. So if we were to come back here, and we have the image loaded. And what we can do essentially is that we can, for example, convert it to monochromatic, to a monochromatic image. So let's call it a gray image. And to do so, you just call cv2 dot convert color. Inside of it, you have to specify the image you want to convert. So we're going to pass in the image, and we're also going to pass into what color space we want to convert. As the handy variables that you can use. So you just write cv2 dot color underscore the type you're right now and what color space you're now to the type that you want to go to. So right now, by default, OpenCV is in BGR. So yeah, it might be counterintuitive. So I said RGB a lot. That's how pictures usually are stored. But OpenCV by default works with BGR. It's the same thing. It's just that the order of the color channels are switched. That's the only difference. And then we're gonna write 2. It's really the number 2, and then we can write what color space we want to go to. So just going to write gray. So if we were to do that, and then let's say we want to display this image, so just going to write image show and wait key, wait key 0. We should be, oops, cv2 image show gray. Am I doing something wrong here? Oh, yes, I forgot to write down the ID of the page, the window. That's a common mistake. So we're just going to call it gray, and that should do the work. So I open up a window, and as you can see, our dog is now actually monochromatic. So it's a value, each pixel has a value between 0 to 255. If I were right now to go inside the, see the shape of the image, which we can do, I'm actually going to type gray.shape. If it actually wants to, I have to close this. Here we go. So right now, it doesn't, so as you remember before, the image itself, it has both the height, the width, and then the 3 color channels. But because now we're monochromatic, there's only 1 channel. It's not even going to display the 1 because it's just 1 single value for a 2D array. So that proves it that we actually went into a monochromatic color space. There's also other color spaces you can go. For example, I said that maybe you want to work with RGB instead of BGR, which might be important for you. So again, color underscore BGR to RGB. This will do the same thing. If I actually were to, let's call this RGB, if I were to actually change here a few parameters and call this, this is on RGB. It might appear weird because OpenCV by default uses, again, it uses BGR. So it's trying to display BGR instead of RGB, which switches around channels, color channels. So that's why it looks kind of weird. For anyone curious about different color spaces, we'll talk a lot about them. Yes, if you're especially in filmmaking, if you ever use stuff, applications such as Adobe Premiere Pro or any editing tool, you're probably already familiar with them. They're very, very much used. Actually, even Photoshop has it. So if you're really interested in knowing more about a more like artistic importance to them, you can always look at those videos online. There's a lot of people talking about them. Does the conversion assume that both spaces need the same number of bits? Yes, especially if it's a free color channel, color space. So I was talking beforehand, for example, let me go back to the slides here. So it's shocking that each different triangle is a different color space, but they all use free color channels. So but the only difference is that if you were to convert it to a different color channel, and let's say that your color itself is somewhere over here, because that as a point, it's represented maybe somewhere over here. If you were to use a different color channel, your other color, the same color, will not be at the same spot. You'll probably need to move it, do some transformation to that point to be able to relocate it somewhere else in the triangle, in the bigger one. But yes, every single at least most color spaces use 8-bit just because it's easy to do. There might be some exceptions, but they're usually very uncommon type of color spaces for very, very specific applications. But for what we're going to use today, we're really not going to have to touch any of these. So assume that's always 8-bit for us. Okay, so we've talked about color spaces. There's also a way for us to actually, if for example, you want a specific color or a specific channel, you can actually split those channels. So that's actually pretty easy to do. So you can call here, you can extract those by calling cv2.split and specifying the image. So this will split the different channels independently. So essentially it's going to be like a monochromatic image, but for a single color channel in specific. So you might only have to work with blue, green, or red. So with that, you can use this command and it will basically split them. Of course, you can always reassemble images. So you might work like independently on a specific color channel, and then you want to merge it back together like to a free channel image. So you can always do that as well. So we're going to call the same image. We're just going to override it. It's not going to change anything because we didn't change the values of the different color channels. So to do this, we're just going to call cv2.merge instead of split, and we're going to create an array where we're going to pass in our different color channels. And this will, like the total net effect will not change anything because again, we didn't change any color channel, but we are able to basically split color channels if necessary and remerge them at any time. So this will not do, oops, we have to restart here. It actually wants to close run. Okay. And if it actually wants to, yeah, it's dead. Okay. Let's call this again. It's actually, yeah, okay, it does nothing essentially because we're not loading any image, but yeah, it's just gonna split it and bring it back together in this case. Let me go back to the slides. Okay, we're a little bit slow, but we'll catch up. Okay, so another important part of computer vision is really about working with mask and bitwise operations. They go together. I'm going to explain exactly what they are. But again, I'll bring back the reference to the editing software that we talked before with that question. So if you ever work with editing software like Adobe or any more advanced editing software, you probably have used masks. So masks are really a way to isolate parts of a picture of a video and add it or subtract it from another piece of media. So as you can see here, we're just in this picture, in this GIF, we're just isolating the actual horse from the overall bigger picture. And then we might be able to change the background and put it to something else. So if you're in VFX or just a general compositing with YouTube, with videos, this is very common to use. This is actually maybe the tool you might have to use most. If actually you know what rotoscoping is, the rotoscoping is about like cutting off a character, like over the contours of the character. This is a way This is actually very painful to do it manually. So actually what we're going to do right now is kind of later on is kind of a little bit like rotoscoping. So we'll actually be able to detect edges and contours, which might be useful for either taking features from the image or actually cutting off the image or creating masks with it. So I was talking about bitwise operations. So if you're any familiar with discrete math, you might see, might look at these truth tables and be like, ah, yes, I remember those. So these are just basic, wait, let me just accept someone in. These are just basic Boolean operations that allow you to do some very basic computer math. So for example, we have the AND operator that basically assumes that if both inputs are true, if they're both 1, then the output is 1. Otherwise, it's always off, it's always 0. Then there's the OR, where only one of the two values have to be 1 and the output will remain 1, otherwise it's 0. We also have XOR, which is another very powerful tool. Yes, Boris has joined the chat. So there's also XOR, which is like OR, but it's an exclusive OR. So if there's only one of the inputs that is 1, then the output is 1. But if 2 of the inputs are 1, the output will be 0. So it's kind of like the OR with a special case. And there's also the trusty NOT operator, which just inverts the input. So why are we talking about bitwise operations? Well, mask acts like bitwise operation or any kind of Boolean algebra that you might have done. So here, as you can see, we have first our dog, and we're applying a mask. So a mask usually is a monochromatic image that is that has values for each pixel from 0 to 255. And when it's white, that means it's equal to 1. And when it's 0, it's kind of like equal to 0. There's also a shading if you want to do like half transparency or stuff like that, like blending and stuff. But usually it's not, especially for computer vision, it's not always necessary. It's more about like cutting that specific object. So here we want to cut the head of our dog. So we're applying this mask where only the white part of the image is taken out of the original dog image, and we're displaying it at the end. And down here we have a little bit more complicated operation. So here we're taking both a dog and a house images, and we're taking only a part of the house image and we're sticking it on the dog image. So let me show you how that actually looks in code and with Opencv. So another person joining in. Let's admit them. So let me just teach a bunch of them here. And what we're going to do is essentially here we're going to import our 2 images. Let's start with 1 image. Let's start with our trusty dog and say that cv2 dot image load. And let's say that we want to load image read, sorry, that's very confusing. Want to read our dog image, so .jpg. And then let's say that we want to apply a filter of it, a kind of mask. So we have to generate a mask first. So what we're going to do is that we're going to generate a blank image, so a completely black image. To do so, again, like I said, NumPy really uses the arrays that we're using are NumPy arrays, so we can use NumPy. That's why we imported it here at the top to actually generate this blank image. To do so, we're just going to generate a blank image by doing, let's say, np.ones. So basically, it's going to be an image just with ones values, and it's going to be a monochromatic image. We just want 1 value per pixel. And let's say that the shape of the image that we want is the shape of the dog image, but without the 3 color channels. So we only want the shape of the image itself and a monochromatic value. So that's what we would want. And let's say that the D type is I think we want definitely is something to do with this thing. So we want it to be an 8-bit integer. So np.uint8. So this will allow us to pick to create a really the values being 0 from 255 inclusively. So if we were to do that and actually show the image, I'm actually going to show you guys how that's a blank image. So image show mask, and if I were to also image show weight key, let's put 0. And if I were to run this, if actually wants to run, yeah, does that again, eh? Yeah, here we go. Let me just restart this. So run, and run. Okay, image show, what's the issue? Oh, again, same issue. So just specify the ID by a string, and it's a blank image. So that's good. Now we're gonna actually draw some white rectangle or any shape on it. Actually, let's go with a circle. I think that's more interesting. So to draw a circle, it's the same thing. It will be the same thing as a rectangle, but you have to specify the appropriate details. So instead of specifying the points of the rectangle, you'll just specify the radius and center. So let's actually do that. I'm going to remove this part. Let's call it this. And to do that, we're just going to call cv2.circle. We're going to pass in the mask, the image that we want to modify. And then we're actually going to also specify the initial position of the circle. So that's done through a tuple, just X and Y. It's quite simple. And then you have to specify the radius. Then you have to specify the color of the circle. So because we're monochromatic, we'll just write 255. But if it were a color channel, you would just create another tuple and specify the 3 color channels. But again, because we're only working with 1 color channel, 255 will suffice. And finally, we'll have to specify the actual filling of the image, the thickness of the image. So I'll just put -1, it will just fill the entire circle. Otherwise, you'll have to specify the thickness of the border of the circle. So if, for example, you want 10 pixel of thickness, you'll just type 10. But if you wanted to fill the circle, just type in 1. Okay, that's good. So we have here our circle that is created. As you can see, it added here the proper image. Let's now print see what changes it made to the mask. So cv2 image show mask mask, and then cv2 dot what was it? Weight key. Let's put weight key 0. So yeah, so here we have a circle. Same thing goes with a rectangle, and you can really put wherever you want. It's fine. And here, yeah, we have here about 100, 100, and also it's 50 radius, so it's about half of where the center is, which is right. And it fills in the circle because we specified -1, and of course it's white. Okay, that's great. So how can we apply this? It's very simple. So to apply it, we have Bitwise operations in Opencv. So I'm going to show you guys. So let's say that we have mask dog, and let's say that we'll call cv2 bitwise underscore and. So this is the and operation that we're performing. So again, reminder n, if they're both equal to 1, if both inputs are 1 in a single, when you overlay both images, both the mask and the dog image, then it will keep that part of the image. Otherwise, it will discard it. So we'll see exactly what I'm trying to say to you now. Oh, because we have to try this, of course. Here we go. Yeah, okay. Okay, interesting. You're right. It works. So specify mask to none and then pass in the mask as that. Okay, excellent. So you can cut the image, and essentially then this acts as its own standalone images. So you can basically do some collage, you could say, with other images by, again, masking them and applying whether either an and or bitwise operation. So an and, again, just to revise. So an and, basically what it does is that both images have to be white, or both images have to be 255 or more than 0, you know. Well, it depends if you want to blend it in, but if it has to be high to actually keep the pixel. Otherwise, you can also do an OR, which basically no matter, as long as one image has something above 0, it will put that pixel in the output. So that's how you can do basically masking and bitwise operation using masks. And also we can also use other techniques. So maybe you're wondering, okay, how could I, apply an image over this image without necessarily, obstructing the image, like with the house here. So what we can do is that we can apply some blending. So that is essentially what you might think about. It's like applying some transparency. It's like making this layer, the dog being a little bit more transparent, and putting it on the house. So that's actually pretty easy to do. So if I were to, let's remove those as well, the dog here, just call this in. And what we can do, we have to close this. Here we go. So what we'll do essentially is that we'll load also a house. So CV2 image read house.jpg. And that's great. What we can do then is that we can blend them. It's actually very easy to blend them. You'll just need to use blend, and you just call well, yeah, you have to make sure one thing before that. I forgot to mention this. So dog and house might not have the same shape. So if I were to actually call both, you would see, oops, let me put print, it'll be easier to spot both of them. So as you can see, they do not have the same shape. They do not have the same size as images. So if you want to apply, if you want to like just oppose them, like in this case, you really have to make them the same size. So either the dog or the house have to be resized. To do so, it's we have to use a special command. So we can resize the house by calling house equals cv2.resize. So cv2 has this handy function to resize images to what size you want to. We'll put in the house image, and we'll specify it to be the same shape as the dog. So dog.shape 1 and dog.shape 0, index 0. So now if you were to actually look at both sizes and compare them, so dog.shape, you'll notice that they have the exact same shape now. So we can work with them and just oppose them or do any collage like that we want without having any troublesome issues. So now how do we actually combine them? So there's this handy cool function that allows us, if I can actually find it here, I have here a list of all the functions. Where is it? I lost it. Yeah, you can add weighted, so it's called cv2.weighted add. So this handy function, where is it? Add weighted. Okay. So if we were to call here blend and call cv2 dot this, then we can specify both the house, specify how much we want to blend it in. So let's say 0.5. Then we want to specify the dog, how much we want to blend in. Comma, let me check here. Yeah, so source alpha, source beta, and then brief calculates missing requirement argument gamma. Let's say, let's actually, if we can actually specify, we can just add, I believe that will suffice. So if we actually check the information for the CV2 add, here, this should do it. We have, actually, no, here it is, gamma, beta, add weighted. Okay, we have to specify, fair enough. So we'll specify this. Okay, and let's image show. Blend. Oops, my bad. I activated too quickly. let's kill it, run it. And here we have to wait key 0. And if we actually look at it, it's actually gonna over just oppose the both images as seen here. So we can close that. Okay, let's go to the next thing. So now it's the cool thing. So we're approaching the machine learning part, the actual interesting stuff. We mostly went through the very, very basic Opencv functions that might allow you to do transformation, but they don't actually allow us to do anything more interesting than that. They're really just tools to allow us to do further operations. So I would like to take a moment. This looks a little bit more out of context. It looks like, oh wow, sudden math equations. What is going to happen? So I want to quickly introduce to you what we call convolutions. So it's a very general mathematical concept used a lot in machine learning and especially in image processing. It's really about blending. You can think of it as blending two functions. So here, the rate, we're essentially creating a new function using two other functions, f and g. So essentially, the second function, as you can see, is inverted and shifted by a constant. And here, what we're trying to do is we're taking this and making it as the rate of our function over a cross-section of the domain. So really, think of it as blending. It's not really important to know exactly how it's used in mathematics that much. It's really, you have to understand that it takes in two functions and blends them together in such a way that it creates something like this. And if you want to use convolutions in a more practical term here with images, we have to slightly modify our formula, because if we consider our pixel of images, our array of pixels, to be kind of like our function, it's already discrete. That means that it doesn't have like an infinite domain with like 0.44, 0.75 pixels. It has very discrete pixels in its array. And so instead of using a integral, we're actually going to use a sum. So in programming, whenever you see a sum, that means that you have to have some sort of for loop, which is pretty much how things are handled in this with sums like this. So and as you can see, the same thing. So we're just multiplying two functions, with the second one being modified at the input. And if we were to work with images, convolutions, it's actually even simpler to understand it. So here I have a small diagram that explains what happens. So in short, imagine we're taking any pixel in our image, and we're looking at its neighbors. Let's call this the filter. It's a kernel of size 3 by 3, so it's a matrix that will define it as being our, sorry, I think I'm confusing both two terms. So this first matrix on top is what we call a kernel. The center pixel is the pixel that we're currently focused on, and the pixels near it are its neighbors. So you can see here that the 0 here is this part, the whitish part. The 226 is the more dark part. So it's really a monochromatic image, because we only have one value between 0 to 255 in this entire image. Then we have another matrix that will define it as our filter. And like I told you a little bit before, our images, our arrays are basically kind of like functions. So here we already have kind of like two functions. We have our image, we have our kernel, and we also have a arbitrary filter. So these values are really where you want it to be. Here, in this case, it's -1, 0, -2, 0.5, and whatever. They don't have to have a specific meaning behind it, as long as the sum of it is equal to 1. If it's not equal to 1, you might need to normalize it by dividing it. If, for example, the sum would be 5 of each of these numbers, you would then need to divide the final product at the end by 5, but we'll see. So what you do with these two functions is that, as the formula explains it, we actually multiply them. So each cell, each respective cell is going to be multiplied. So 0 is going to be multiplied by +1. Then we're going to sum this with the next cell, 64, which is going to be multiplied by 0. Then we're going to sum it with the next next cell. 128 is going to be multiplied by -2, etc., etc. And you're going to end up with this huge sum. Essentially, the sum is represented by this summing annotation. So it's really a sum of different products. Be careful, this is not a product sum, so it's not. It might look like some mathematical operations with matrices or vectors that you're already familiar with, but it's not the same thing. It's really different. It's what we call convolution, and it does something completely different, which we'll see. The filter values are arbitrarily defined, yes. But certain filters, certain values have different effects on the image, which we'll see. And these filters actually these effects that it has are widely, drastically different, and might give us different output results, which we'll see really soon. So one of these application is blurs. So again, if you're very familiar with Photoshop or any editing software, you probably know what is a blur, and especially you probably heard of the term Gaussian blur. So this is a very, very popular blur, and a blur just makes it so that the image gets a little bit more distorted, gets a little bit more unfocused. What it actually does is that it reduces the amount of details in the image. So if there was a lot of noise, for example, on the floor or on the head of the dog because of the hair, Gaussian blur or any type of blur would basically reduce that noise and make it a lot more smooth. So actually, I wanted us to try to implement this. It's actually very simple. And to do so, we're just going to open up, where is the, okay, here we go. Yeah. So I'm just going to delete all these. And what we're going to do is that we're going to implement this, this whole process, this whole convolution, and was going to apply a specific Gaussian blur. So again, for this to work, we're gonna have to define two things. At first, we're gonna first have to define our kernels and our filter definition. So let's actually do this. So what I'm gonna do is I'm also gonna import here just for facility. You may have already used this library before, but matplotlib and pyplot splot. So again, this oops, I have it closed. Okay, here we go. Okay, so this will allow us to basically, instead of using the Opencv window, we're directly going to be able to draw here on this on Jupyter Notebook. So what we're going to do first is that we're going to define our filter. So let's say filter is equal to np.array, and let's define it. So it's a 3x3 array. It can technically be bigger than that, which might have, for example, a bigger influence, like a bigger Gaussian effect blur. Maybe it'll blur your image even more. But the rule of thumb is that your array has, your matrix has to be an odd number of in size. So it can only be 3x3, 5x5, 7x7, etc., etc. It cannot be, for example, 4x4. That would be illegal. The reason behind that is because you would have, how would you define the center pixel in your kernel? So again, because you have to add, you're defining two sub-functions, let's say, and because you're applying this on every single pixel, you have to figure out what is the center pixel. So that's why it has to be an odd number in size, because if it were even, you would not be able to decide which pixel is the center one. So again, let's define our array. So for Gaussian blur, there's a specific one for it to work. So it's, I believe, let's check. I believe it's minus. We can actually look at Gaussian blur filter definition. If we go on the official website on Wikipedia, I believe I know it, but I want to make sure. Yeah, this is the one. So 1, 2, okay, yeah. So here there's 1, 2, 1, 2, 4, 2, 1, 2, 1. This is okay. And I think you can also use negative numbers to, let's actually do it with negative numbers. No, let's keep it with positive. It'll be easier for people to understand. So we're just gonna copy it down here. But because we have, again, a sum, because if we sum up every single number in this array, we're gonna have something bigger than 1. We're gonna have to divide it by a constant, which is 16, but we'll see later on how that works. So 2, 4, 2, and 1, 2, 1. So this is our array definition, filter definition. So we're just going to go to the next thing. So now we have to basically, we'll read in our image that we want to apply the blur on. So I'm going to apply the blur on the dog. So we're going to call cv2 image read dog.jpg. And we're going to also basically change the color space of this image to make it monochrome. That will help us reduce the amount of work we have to do on the image. Instead of working on 3 different channels, we'll just work on one single one, the gray one, from 0 to 255, which will greatly decrease our amount of work. So convert color, and we're going to specify the image and the color conversion that we want. So BGR to gray. Okay, excellent. Now what we have to do is that we essentially have to create the filtered image, the blank filter image. So we're not going to overwrite this image. We're going to work on a different blank image instead, and we're going to put the final blur result on that blank image. So to do so, I have here a few code. I'll call it. Here we go. So we're just going to create the shape of the gray image. We're gonna both define, this is to get the size of the kernel that we want. So in this case, it's gonna be equal to 1 for both of them. So it's basically kind of like the radius of the image. So 1 for each side. And this is our blank image. So I'm gonna call it blur. So this is for now, it's a blank image, but at some point we're going to populate it with the actual Gaussian blur that we created. So let's define this as so. And right now what we have to do is that we have to, if I go back here, we have to loop through every single pixel in our gray image and essentially define the get the neighbors of the current pixel and apply the filter definition on them to essentially get the new pixel value using this formula for the convolution. So to do so, we're just gonna do for x in range 1, the width of the image -1. So why am I doing it so? Just because this is to basically solve an edge case. The problem is that if we were to start with the very first pixel at a corner or really at a border, it would be problematic because we would not be able to get the left side or top side or right side or bottom side neighbors. So for example, if it were really, really at the top left, you would only be able to get these 3 pixels at the bottom, and the left side and top side pixels you will not be able to get them. So to avoid this, we're just gonna ignore the border pixels and the corner ones and work directly with the ones after, which is one way of handling it. You could maybe you could get these pixels from the other side, or you could do some fancy trick to actually be able to work with these corner ones, but sometimes it's not necessary. We just want to get an overall blur. So this, we won't bother with working with the edge cases. So I'm actually going to call this I for j in range. Let's call this again. We're avoiding the edge cases, so we're starting with 1 and we're ending just before the last pixel of the row or column. And what we're doing is that we're going to create our kernel. So our kernel again is this. So we're defining this kernel as being the neighboring pixel and the pixel that we want to focus on. So I and j are both the coordinates of the pixel that we're interested on, but we have to get its neighbors. To do so, we can use this fancy trick that, if you're familiar with NumPy, allows you to take ranges in the bigger array. So essentially, it's kind of like if we were able to crop the image, the bigger image, and crop it in a 3x3 image, crop a 3x3 portion of that bigger image. So that's what we're doing right now. So we're doing I minus kernel w x plus kernel w plus 1 And now, so this is the first corner of our image. Now we have to define of our crop. Now I have to define the opposite corner of our crop to essentially get that 3 by 3. So J minus kernel H and J plus kernel H plus 1. Okay. And then we're going to multiply this by the filter. So essentially what it's going to do is that it's going to do exactly what it's doing here down for the new pixel value. So it's going to multiply -1 with 0, 0 with 64, 128 with -2, and it's all essentially it's going to combine these together. And what we'll do next is that we'll sum it up. So we'll sum every single, after the multiplication is done, we'll sum every single new value that was generated into a new pixel value. So we'll call it sum, and we're just going to say, again, NumPy has a very cool feature for that. So just np.sum, and it's going to sum every single component of that array. So we're just going to pass in the kernel. And next, what we're going to do is that because our image has to be restricted with values between 0 to 255, we have to make sure that they don't go above these values. So we're just going to create some very basic if cases here. So if sum is smaller than 0, we're going to make sum equal to 0, else, no, not going to put an else. Let's say if sum is greater than 255, what we're going to do is that we're going to restrict it to 255 at most. We'll just make sure that it doesn't go above these values. And finally, what we'll do is that we'll draw on our new blank image. So remember that we create this blank canvas. We're going to draw our new pixels in it, the blurred ones. So I'm just going to specify these and put in the sum. Okay, great. So now we should be able to actually get the image. So let's display our image. So instead of using Opencv's image window, I'm going to use matplotlib, the pyplot, which will directly show the image here in our notebook. So I'm going to call imshow, and I'm going to pass in the filtered, the blur image. And I'm also going to specify that it's a gray, it's a monochromatic image. So CMap equals gray. That will just make sure that it will properly display the image how we want it to. So let's call this. Okay, there seems to be, oh, okay, there seems to be a typo. No issue. And here it's not X, it's I. Okay, let's try this. It's going to take a second. Okay, it seems that there was an issue. Oh, yeah, okay. So I said here at the beginning that the sum of these elements of this array has to be equal to 1. In this case, in this specific case, it's not true. As you can see, this is well above 1. So what we have to do is that we have to apply a coefficient to the sum to make sure that we normalize it back to 1. So because it's 16, the sum, here at the when we divide it by the sum, we're just going to divide it by let's say 16. So I'm doing double slash. That just means it's an integer division. It's not going to give me a floating point number. Okay, let's try this. Okay, yeah, there seems to be a small blur to the image already. Let me see if I can actually make you guys have a comparison. So I don't know if it's visible, but there is definitely a blur that was applied to the image, as you can see. So this is a 3x3 blur. If we wanted to increase the amount of blur, we would need to make it, in this case, 5x5 or 7x7 or et cetera. It's just that the filter will slightly be different. It will not be these numbers. You would have to adapt them to fit these. And as well as the coefficient would need to be different because the sum of the numbers inside would be different. So this is how convolution works and how you can apply a great number of effects on your image. So here we use it specifically for Gaussian blur, but Gaussian blur is not the main, it's one of the main features you can do, main filters you can apply, but there's many more other useful filters that we're going to have. So one other is the edge detection. So this is another very powerful tool that essentially allows us to find the very edges of our objects in our image. So for example, here the dog, we can definitely see that it crops it out really well. And this can be done by the same algorithm that we defined here, just by changing the filter. But the sad thing here is that it would be boring to do this every single time we want to have apply a filter on our image. So Opencv has actually some very handy tools to make it a lot easier for us. So what we're going to do here is that I'm actually going to define a new cell, and I'm going to show you what Opencv has some tools to solve this issue, to do it for us, essentially, to do it in a one-liner, as they say. So the commands that we can use for those are actually, let me get that for you. So let's start with blurs. So Opencv has an inbuilt way of doing blurs. You can call blur equals CV Gaussian blur. And we just pass in the image. So I'm going to pass in, you know what? I'm going to pass the image itself, not the gray image, because it will automatically handle the other color channels without any issue. So let me then define two other parameters. Actually, yes. So we have to define the kernel size. So here we're using a 3x3 kernel, but we can also use other kernels. Let's start with a 3x3 actually, because that's what we implemented. So we'll have a comparison. And also we need a standard deviation. So you don't have to worry that much about the standard deviation. I usually keep it automatic. So if you wanted to make it to handle itself, the standard deviation, just put in 0, and that would do the trick. So now if I were to execute, if I were to display this, so CV2 image show blur, and let's pass in the blur image and CV2.wait key 0, we should be able to see the actual image, our blurred image appear. So it seems to be the case, but let's apply it. Let's put it stronger. Let's put it something like 15, 15. So that's a lot, actually, but it should be able to work. Yeah, as you can see, the image is a lot more blurred. And you can always increase these numbers as much as you want. The idea behind blur, again, is that we are able to reduce the amount of details in the image. So it really hides all the details in the texture to make it as simple as possible for maybe our edge detection algorithm. Because the problem is that maybe when you try to detect the edges in your image, it might detect a little bit too many edges. For example, these lines here might not be useful. So a way to handle them would be to blur your image a lot more so that you can extract only the very, very strong edges in your image. So that would be a very powerful use of the Gaussian blur in combination with the edge detection. Okay, so we're reaching, I see time is really passing fast. So right now we'll go to the final part of the presentation. I think it's the most interesting part of the workshop. It's convolutional neural networks, and especially for image classification. So basically we'll train a model to be able to recognize specific images. Let me come back here. Let me delete a bunch of stuff here. Okay. Okay, so we're not going to import Opencv for this because we're going to use a data set already of images. So at this point, I hope that you all have installed TensorFlow on your computer. We're going to use it to essentially train our model, and TensorFlow itself has already some inbuilt databases of images that we can use to train our model. Because as you might know, deep learning usually requires a lot of training data. So this specific database has it all already for you. You won't need to download it or make it yourself, which can be very painful. This is really a testing package for it. So we're going to import a few very important libraries. So we're going to keep NumPy. We're going to keep matplotlib, but we're also going to import TensorFlow. So import TensorFlow STF. We're also going to import from TensorFlow again TensorFlow import Keras. So Keras will help us create our deep learning model. You'll see later. And that should be about it. Let's call it like that. Okay. What we're gonna do next is that we're gonna import our libraries, a data set. So we're gonna use something called MNIST fashion. So you may have heard of it. Actually, I'm gonna show you if I can fashion. So this is essentially a huge data set, a huge database where you'll be able to find a lot of fashion items. So that includes shoes, that includes coats, that includes dresses and shirts and whatever. So it has about 10 items and it has over 60,000 examples of images that we can train our model with. So we're going to use this to create basically a classification deep learning model that will allow us to basically classify what object we're looking at, whether it's a shoe or a t-shirt, whatever item we have. So we're going to first import this data set. So it's actually very simple. We don't need to download anything as long as we have TensorFlow installed. To do so, we're going to call it fashion. This will be our data set. And we're going to say keras.datasets.fashion_MNIST. So this will import it for us. And just underneath it, we're going to separate this data into 4 groups. Well, 2 groups, but each group is like subdivided a little bit. So we have first our training data, and we also have our testing data. Our training data will basically be used to train our model, and our testing ones will be used at the end to verify how accurate is our model. Each of these 2 groups has 2 subgroups. One is the actual input, the images, the fashion items, and the other is the labels. So what are the actual, what is actually in the image? So basically a tag. So this tag is usually an integer. In this case, because we only have 10 fashion items in this data set, it's going to be, every image is going to be associated with a number from 0 to 9, representing what fashion item it is. So let's actually divide this data. So we'll call it import train images, train labels. And here we're going to call test images and test labels. So labels dictate what is in the image, and the image is the actual array image. So in this data set, also I have to mention that the images are 28 by 28. So they're really small. The reason why they're so small is because we don't want to wait two entire days to train our model. We really want to wait like max 5 minutes. So that's why they're so small, and they're also monochromatic. Again, because if you're able to do it monochromatically, you're able to do it with multiple channels as well, multiple color channels. So let's say here fashion dot load data. So this is basically going to load our data. Let's load it. Okay, it's done. If you actually want to see if it worked, we can do that quite easily. So what we'll do is POT dot image show. So we're going to basically draw the first image in the trained images to see if it actually imported properly the image. So I'm going to take the array trained images, and I'm going to take the first image from that array. I'm going to make it appear, and we're supposed to see it, yeah, appear. So this appears to be some kind of shoe, some boot. We'll actually see later on what it means, what exactly it is, what exactly is the name that it was defined with. But we can see that it properly imported every single every single images from the data set. Actually, if you want to see how big the array is, we can actually do train images underscore shape, which will show us that we have about 60,000 images. They're 28 by 28. So yeah, there's a lot of pixels here, but that's good because we can train our model properly. Okay, that's good. Let's now define, I'm going to import here something. So I have here a dictionary that basically associates a number with a string. As I said before, the training labels are strings. They're not text. They're not, sorry, they're not strings. Sorry, they're integers. They're not text. They're not string. The reason for that is because, well, computers are not really good with handling text. So when you can, they really much prefer to work with numbers. And that's why when we try to feed our algorithm, we try to avoid putting in text. We rather want to put in integers. So that's the reason why. It's also if, for example, you were to have your model might need to support multiple languages, you can associate one integer with multiple strings or multiple languages for the same string. So it might be another equivalent name from French or Mandarin or whatever other language. So yeah, I'm just going to import this dictionary. I'm also going to put it in the chat if you want to. So this is specific for this data set. It was already made in advance for it. Okay, so now it's time to train our model, to create our model, sorry. So to create our model is actually very simple because we have Keras. Keras is a special tool included in TensorFlow that basically allows us to stack a model to create it step by step. Now actually I'm going to show you. So we'll create a variable and call it keras.sequential. Sequential, it means that we're going to have a series of action for our model. So when we're going to put an input on our model, it's going to go through a set of actions and it's going to deliver an output at the end. So that's what sequential is. It's really a set of actions that we're going to define. So I'm going to open up a new array, and inside this array, I'm going to define a few things. So one advantage of convolution and doing that with images is that we can basically extract information from the image. As seen previously, here I was able to extract edges, and here I was able to reduce noise with the blur. And that's very useful because what we can do is that if we are able to apply this on images before we feed them to the neural network, it will basically simplify the work that our neural network has to do. It will only keep the important information that we want to analyze. That means really the edges. When you look at an object, you're able to distinguish that object from its differences with the environment. So that's what the edges allow us to perceive from the image. And so that's why we can use convolutions in our model. So I'm going to write here a line of code, and I'm going to explain later what it does. So we can import a convolutionary input, a node here. So we're going to say that it has 64 filters, and it's 3 by 3. Okay, I'm going to explain what it does here. So this specific layer of the model of the neural network is going to create 64 filters. So remember again, as we saw before, filters are this. So this arbitrary number is a matrix that we define. Our neural network is going to create 64 random instances of it. So the actual values that we're going to see in the filters of the 64 3 by 3 matrices are going to be random. So this might be whatever floating point number that it wants. It's going to generate randomly. And we want them to be 3 by 3. That's the size of the filter. And we also want to create an activation tf.nn value. So this is just how the next layer is going to be approached in the neural network. So after it passes through a filter, let's say that the filter turns out to be something like an edge detection filter, then it's able to extract the contours of the image. That's good. So depending on if it applies the activation function, it will pass it to the next layer. So this ReLU activation is just a special function that checks whether the value is above 0 or not. If it's above 0, it will not pass it. If it's above 0, it will pass it to the next layer. It will probably activate the next layer. So I'm also going to specify the input shape of our image. So because our image is 28 by 28, I'm going to specify it like so. So it's 28 by 28 with one brightness value. So it's one channel, one color channel. So I'll just put 1. So that will just help the model better recognize what input data it has to work with. Okay. The next filter I'm going to work with is called a max pooling. So max pooling sounds a little bit complicated, but it's really not. It's actually maybe the simplest thing in this model. If I were to go back here to my PowerPoint and show you this, so this is max pooling. What it does is basically shrinks the image and keeps and amplifies the data inside the image. So let's say our image was 4x4. What it would do is that it would divide our image in 4 parts and take from the 4 pixels, from the 4 quadrants, it will basically take the brightest pixel from that quadrant and pass it to the output. So it will shrink the image and amplify the brightest pixels in that image. So that's what max pooling does. In this case, what it does is that it will basically amplify, if for example, it detected edges in the convolutionary layer, it will basically amplify the presence of those edges. It will make it more obvious for the program, for the model, that these edges are present and that they're important. So next, what we're gonna do is that we're gonna flatten the input. So because these two layers work with images, they're 2x2 in size. So again, width, height, and the brightness value, that one color channel. But if we want to pass it then through like some neural network, we have to flatten it. So that means that instead of being 2x2, we're going to reshape it to a one-dimensional array. So it's going to be one long sequence of all the pixels one after the other. So to do so, we can use the flatten layer, which will help us do that. And then we can actually build some neurons. So in Keras and TensorFlow in general, it's very easy to do so. You just have to specify how many you want, how many neurons. So let's say that this layer will have 128 neurons. So, this is the very basic part of our model. So just a bunch of neurons interconnected with each other that will decide what to do. And we're also going to specify some activation function. So we're going to keep it the same. We're going to still define it as a value. So again, reminder, if it's less than 0, it will output 0. If it's larger than 0, it will output that value that is larger than 0. Let's do the same thing, but now let's reduce the dimension of the last layer in our model. So we're going to reduce this to 10. Why are we reducing it to 10? Because we have 10 outputs. So ideally is that we start with a lot of inputs, a lot of like neurons, and we slowly tunnel it down to the number of outputs that we want. And because we only have 10 possible outputs, we want the output to be of 10. So the output of this model is basically going to be 10, an array of 10 values, and that value is basically going to define how likely the how likely that item is what it says it is. So for example, this value might be higher in the array that is 10 of size 10. The 0 index might be higher than the 1. That means that it's more likely that the item that it detected is a t-shirt rather than a trouser. So here, let's see. So what we can do here, instead of putting like an activation value, let's try to rename it to softmax. Softmax will just normalize it. So the sum of all of the 10 item array is going to be made equal to 1, so that we have really a probability of 1 in total, and the probability of being one of the 10 items is 1. So we want the sum of all the items here, the probability to be equal to 1. So that's what softmax does. Okay. Finally, before calling this model finished, we're just gonna add more convolutionary layers. The reason to do that is because we want to extract more information from the image. So that's what we're gonna do. But we're gonna keep it the same, but we're just gonna remove this input shape because that's no longer the case. So just after our first convolutionary layer and our max pooling, we're gonna add another copy of it. So this will make it that it will run a lot better. It will be more accurate over time. Okay, that's great. So we define our neural network. Let's now train our model and see the results. So I'm going to copy here some code, and I'm going to explain what it does. Here we go. So this will basically train our model. It's that simple without this even. So we're just going to compile a model, say what optimizer it's going to use, and what loss function it's going to use. So this is just to measure how good the model is performing. And we're also keeping track of the accuracy, so we want to keep track of that metric. Then we're going to fit our model with our current training data. So we have to specify those. So training images, the labels, and how many epochs, so how many runs do we want it to train it. So we specify 5 here. This is arbitrary. It's really might be better, might be worse, depending on what you want to do. Okay, that's great. So let's try to run this and see. So this might take like 2 or 3 minutes. So we'll wait. If there's any question meantime, feel free to ask them. So yeah, it's going to take about 5 minutes at most. You can actually see here the loss and the accuracy live. So right now it's about 75% accurate. This model can reach about almost 90% if it's properly trained. So we'll see what's the final accuracy after if it's it trains through the 5 epochs that it's supposed to. And afterwards, what we can do is that we can actually test. We'll be able to test our model. So we'll call in this thing. So model.evaluate, and we're going to pass our testing images and our testing labels. So this will do an independent test on our current model when it finishes solving itself. And it will give us information about how accurate it is with new data that it never saw. So remember here at the beginning that we divided our data into 2 sets, the training set and the testing set. The model itself, when it was trained, it never saw the testing set. That's important because this will allow us afterwards to determine how accurate the model is with new data that it never saw before. If we just make it train with a set of data that it knows already and we test it with that data, it will not be very useful for us because we won't know how accurate the model is actually because it was trained on that data. So it already saw that data before, so it doesn't give us any indication whether it's good or bad. But if we feed it with new testing images, then we can properly evaluate whether it's a good model or one that is weaker. So we'll just wait. It's 3/5 of the way. So it's going pretty well. And as you can see, it already reached about 90% accuracy, which is pretty good. If there were a few other features optimized here, maybe could reach 95, but 90 is already a very good score. So let's hope it will be kept the same when we test it with our testing data. Okay. Almost there. It's doing the final epoch. And let's actually put some printing stuff here to print the results. So we'll actually print the results. So this will indicate to us how accurate it is. Almost done. By the way, when this model is trained, you can always save it in the end. So you won't need to train it every single time if you want to, if you want to use it afterwards in your final project or something. Okay, let's try to evaluate it. So it's evaluating. Okay, so we got here, the first value is the loss. And the second value is the accuracy in percent. If you multiply by 100, it will give you 88.9%. So about 89% accurate. So it's actually very close of the accuracy we had in the training. So that means that it's a pretty reliable model that we can use to test new data. We can actually test that. So we're actually going to test the first image. So I'm actually going to print the first image. So reminder, I'm going to show you guys first the image. So plt.image show, and I'm going to look into test images, and I'm going to test the second image of that testing because we never saw it before. So let's see how it looks. So plt.show. Okay, so this seems to be the image. So if we look here, what it could be, it's either a t-shirt. No, it's not a t-shirt. It's a pullover, a trouser, pullover, I think. That's what it is, or a code maybe? It might be a code. Let's see what the model predicts it is. So to predict, we'll just do predictions, and we'll do model dot predict. And inside, we're going to specify the image we want to predict. So the second image, as we displayed here. And we also want to reshape it. The reason why we want to reshape it is because the model was trained with an array of images rather than just a single image. So we have to reshape our input to the model to be what the model expects it to be instead of like a single image. So that's kind of cumbersome, but it's easy to fix. So we just call here reshape, and we're going to put 1, 28, 28. So essentially what it's going to do is that it's going to be an array of images that has only one image with size 28 by 28. That's what it does here when I call reshape. So if you don't do that, it will probably give you an error. So it's a mistake that can really happen. And I'm going to here print the predictions. So let's say predictions. So this will give us an array of size 10 with very small, probably very small numbers in it, floating point numbers that will indicate how likely a it is the item is to be one of those 10 here. So actually let's try it to see what it gives us. So yeah, so there's 10 items here, 10 numbers, and each number represents how likely it is to be one of those here in this dictionary. So the first one, for example, is very unlikely. As you can see, it's 10 to the power -7. So it's very unlikely it's a t-shirt according to the model. But if we look at this one, so the third one, it's e to the power of -1. That seems to be the biggest number in this list, and that seems to be a pullover. So according to the model, this is a pullover. So actually, if I want to print the actual string itself, what we can do is that we can say print I am a, and then you can specify what you want to print. So let's say we're going to use the dictionary to actually convert the number to the name, to the string. And inside, what we're going to do is that we're going to use a special NumPy function called np.argmax. So what it's going to do is that it's going to pick the highest number in this array, and it's going to return the index of that number. So if I put in predictions, it's supposed to print what we're a pullover, essentially. Correct. Yeah, I am a pullover. So it predicted accurately what our object was supposed to be. And if you want to play around, you can also test other objects in this in this data set. So remember the 60,000 images. So there's a lot to play with. Actually, let's pick a random one, 100. If I were to run this, yeah, I don't know what this is, to be honest. Looks like some kind of dress, I would say, but I'm not sure. What are your guesses? So let's do the same here. Let's see what it predicts. So let's run this. And let's run this again. I am a dress. Yeah. Okay. So it determined that this is a dress. Yeah. So that's about it with convolutional neural networks. So I really encourage you guys to play around with this, and especially this data set is really good if you want to test. And yeah, what's next? So we used convolutional neural networks to develop object detection. Sorry, this is not an object. Yeah, it's an object classification, I would say. Classification algorithm. But if we want to determine like the location of the object in the image, what we did will not suffice. We need a little bit to be a little more to take a better approach for this. So there's algorithms such as YOLO. You only look once. So that's what it stands for. So this is an algorithm that does about what we do. It's very similar to what we did, but it's also capable of locating the position of the image, of the object in the image. So that might be useful if you're doing, for example, if you're trying to locate yourself in an environment, that's something that you must have. And finally, some other useful tools, because no one ever wants to always do something from scratch. There's a lot of tools that allow you to simplify the workflow. There's label image. So this is a tool that allows you to create some YOLO models. So you just put in a set of images in the application, and you basically select what you wanted to recognize, and it will automatically train a model to detect the specific objects that you trained it with. And finally, there's also the MediaPipe library that is also available in Python. And it has a bunch of cool models that allow you to do, for example, to detect your movement, to detect your face and shape of your face, to detect the movement of your hands, and also a bunch of object detection. It also has that. So very powerful libraries that are very optimized. This specific one, MediaPipe, is made by Google. So if you ever do any projects, like it's a very quick way of implementing some powerful object recognition, or human body movement recognition if you want to. Yeah, oops. That's about it. I know this presentation was a bit long. It was 2 hours, a bit more expected, and we had some little technical issues. But I hope you were able to learn something, and you'll be able to maybe apply it to some final project at the end of the month. I'm actually very excited to see what you guys are capable of doing. So yeah, if there's any question, let me know. I'm actually gonna end the sharing. So if you want to actually speak, you can speak and you won't be recorded. So let me end it.